record to the cloud, I guess.
Yeah, got it. Perfect.
Okay.
Okay, great. Okay, thanks, Tristan. So please tell us about mirror symmetry.
Okay, all right. Well, thanks. Thank you for the invitation. So I'm going to talk about some work with Adam Jacob and Yushen Lin, which has been, it's a sort of a series of papers the last couple of years about SYZ mirror symmetry for Del Pezzo surfaces and rational elliptic surfaces. So these are kind of classical algebra geometric and differential geometric objects. And the goal is just to understand how much one can say about mirror symmetry for these objects. So the plan for the talk is I'll just recall what Del Pezzo surfaces and rational elliptic surfaces are. So probably well known to most of the people in the audience. And then I want to discuss why mirror symmetry in its sort of Strominger-Yau-Zaslow formulation should apply. And then I want to discuss the results. So existence of SYZ fibrations and some applications for Del Pezzo surfaces. And then sort of the same results for rational elliptic surfaces with a special type of singular fiber. And then I want to describe some applications to understanding Hodge numbers for these pairs. Okay, so let me remind you. So a projective surface is Del Pezzo if the anticanonical bundle is ample. So these are classified, well understood. So you have either P1 cross P1 or P2 blown up at some number less than 9 generic points. And in this case, the Del Pezzo surface is essentially classified up to deformation by its degree, except for degree 8, which is the case where you have P1 cross P1 or blow up a P2 in a point. Okay, so there's up to deformation, not so many of these objects, but still they're quite rich geometrically. So one sort of trivial point, but which is important, is that all these Del Pezzo surfaces have some smooth divisor in their anticanonical linear system. So I will use that freely. Okay, so these are Del Pezzo surfaces, pretty well understood. Rational elliptic surfaces, on the other hand, may be slightly more exotic. So a rational elliptic surface is a surface admitting a relatively minimal elliptic vibration. So it's a surface with a map to P1 whose fibers are elliptic curves and which are minimal. So there's no -1 curves in the fibers. And such that it admits a global holomorphic section. So a map from P1 to Y, which meets each fiber in a point. So equivalently, you can construct these objects by blowing up P2 at the base points of a pencil of cubics. So you take 2 cubics, these intersect in 9 points generically, so choose your cubics nicely. And now if you blow up those 9 points, you get something which is fibered by the linear system, fibered onto P1 by the linear system of those 2 cubics after pulling back. So in this case, the anticanonical bundle is effective, but not ample. And the fibers of this map to P1 are exactly the elements of the anticanonical linear system. Okay. So these vibrations, of course, have singular fibers, and they're all classified by the sort of fundamental work of Kodaira from a while ago. And the classification is kind of complicated. There are many different examples that can occur, but I want to focus on one specific type for the purposes of this talk. This is really going to be the only one that's important, which is a singular fiber of type IK. So this is we call a wheel of K -2 rational curves. If K is bigger than 2, it's a nodal rational curve if K is 1, and it's a smooth fiber if K is 0. So let me Let me just draw a picture of this. Get rid of that. Okay. So, so one way that a torus can degenerate, so we have an elliptic curve, torus. So one way that this can degenerate is you can choose some number of cycles, so curves. So let me draw 3. And this can degenerate by pinching off these cycles. So what happens is you get a torus where, see if I can draw this. Something like this, maybe. So these curves get shorter and shorter. And what you end up with in the limit is something which looks like 3 nodal spheres, which intersect at these points. So these are all S2s. Show these as an S2, or in other words, P1. And they have these 3 intersection points here, here, and here. So in terms of the sort of schematic picture, in terms of the divisors, this would look something like this, where each of these is now, just from the intersection theory, each of these is a -2 rational curve. Okay, so this is the kind of singular fiber that's going to play an important role in this talk. So these are quite common. Oops. Okay, so those are the objects these are the sort of characters in the story that I want to talk about. So each of these objects can be viewed as giving rise to a sort of non-compact Calabi-Yau manifold. So in both of these cases, because you have this, if you take any divisor in the anticanonical linear system and take the corresponding section, which cuts out that divisor, and then you invert that section, you get a holomorphic top form on the complement of D, which has a simple pole on D. So in particular, that you can think of this, the complement Y minus D, as having trivial canonical bundle. So in particular, it's a natural example of a non-compact Calabi-Yau manifold. But it's sort of important to note that the existence of a Ricci flat Kähler metric, so that's what we typically think of when we talk about Calabi-Yau manifolds, they admit these special metrics. So in this case, the existence does not follow from Yau's theorem because this manifold is non-compact. So they're sort of algebraically or complex analytically Calabi-Yau, but maybe not differential geometrically, at least yet. So what about mirror symmetry? So what is mirror symmetry? So first of all, mirror symmetry is some duality between Calabi-Yau manifolds. And roughly speaking, sort of heuristically, what it's supposed to do is relate complex geometry on one of these Calabi-Yau manifolds to symplectic geometry on the mirror dual, and vice versa. So this is a sort of schematic picture of what mirror symmetry is supposed to do. But let me give a sort of more precise instantiation of this principle, which is on X, we can study the complex moduli of Calabi-Yau structures on X. And this is supposed to be mirror dual to the symplectic moduli of Calabi-Yau, or the moduli of symplectic Calabi-Yau structures on the mirror dual. So now we can compare the dimensions of these two spaces. So on the one side, the complex moduli of Calabi-Yau structures on X is computed using Tian-Todorov's theorem. So that's Hn minus 1, 1, this Bott-Chern homology group. And on the other side, the symplectic moduli by Yau's theorem is just equal to the Kähler cone, or the ample cone, which has dimension H11. So in particular, we get this, there should be dimensions here, but anyways, or maybe they should be small h's. We get this relationship between the Hodge numbers. So hn minus 1, 1 of x should be equal to h11 of its mirror dual. So this is a particular case of mirror symmetry for Hodge diamonds. So if you look at the Hodge diamond and you imagine some reflection about an axis, which gives you this symmetry, which sends hn minus 1, 1 to h11, then you will recover the mirror symmetry for Hodge diamonds, which was originally why this symmetry was called mirror symmetry, because of its exchanging of Hodge numbers. So, so this is this sort of schematic picture for mirror symmetry. But at this point, sort of interpreting how we should really think about mirror symmetry, there are several different approaches which live at different levels of detail. So let me give a few of these. So there's sort of maybe the roughest form, which is Hodge theoretic mirror symmetry, which asks to construct pairs of Calabi-Yau manifolds for which the Hodge diamonds are mirror symmetric. So in the sense that they exchange these Hodge numbers. So this is, you could say maybe topological mirror symmetry or something like that. So then there's homological mirror symmetry, which was originally proposed by Kontsevich, which says that the right way to think about mirror symmetry is that x and x check should be mirror dual if the derived category of coherent sheaves on X, so that's a complex geometric object, is equal to the derived Fukaya category on the mirror. So that's a symplectic geometric object. So this is another way of interpreting mirror symmetry, which is more detailed than topological, but still sort of homological or algebraic in some sense. But the basic proposal for how to actually construct these mirror symmetric pairs goes back to the work of Strominger, Yau, and Zaslow, which I want to just explain what their conjecture is supposed to say. And then there are also programs of Gross-Siebert and Kontsevich-Slogelman, which are aimed at using this SYZ philosophy to construct often sort of formal algebraic mirrors. So I won't go into this much, but this is also a big and important area in mirror symmetry. So what is SYZ mirror symmetry? So I have to first tell you what a special Lagrangian is, and then I can talk about SYZ mirror symmetry. So the definition of special Lagrangian goes back to the work of Harvey and Lawson on calibrated submanifolds. So if you start with a Calabi-Yau manifold with some holomorphic volume form, and you take a possibly immersed submanifold, then we say that it's special Lagrangian if, first of all, it's Lagrangian, so it annihilates the symplectic form. And secondly, it's calibrated by this holomorphic volume form. So in other words, after you possibly rotate this complex volume form by a unit complex number, which is constant, then the imaginary part of this thing vanishes when you restrict to L. So in other words, that's the same as saying that the real part of this rotated complex volume form is equal to the Riemannian volume form. So the original interest in these was that these special Lagrangian submanifolds are automatically volume minimizing in their homology class, so in particular minimal. And that was maybe the original interest of Harvey and Lawson, was to find examples of volume minimizing submanifolds. And it's important to note that the notion also makes sense. I mean, when I talk about the definition here, that there's no reason necessarily to impose the Monge-Ampere equation, or that the Calabi-Yau metric is Ricci flat, or the symplectic form has anything to do with the Ricci flat metric. But in that, so you can still make sense of this definition, but in that case, the Calabi-Yau, or in that case, these manifolds are no longer volume minimizing. So then you sort of lose the differential geometric interpretation of being special Lagrangian. Okay. So what does the SYZ conjecture predict? So the SYZ conjecture says that if you start with a Calabi-Yau manifold whose complex structure is sufficiently close to a large complex structure limit, which is something that I won't really talk about, but basically the complex structure is sufficiently degenerate in some sense, then this Calabi-Yau manifold should admit a special Lagrangian torus vibration onto some base B. And in this case, B inherits, oh, sorry, I have to stop touching this button on my pencil. In this case, B inherits two affine structures from this special Lagrangian vibration. It inherits a symplectic affine structure and a complex affine structure. So the mere Calabi-Yau then is constructed by something called T-duality along the fibers, which means that you just take the torus fibers of this vibration of X onto B and you take the dual torus. So that makes sense for all the smooth fibers. What happens with the singular fibers is a little less clear, but you take T-duality along the fibers, and then that is supposed to compactify to the mere Calabi-Yau manifold. So in particular, this X check also admits a special Lagrangian torus vibration onto the same base B. And then one way to interpret what this T-duality is really doing is to say that that the complex affine structure on B coming from X should be equal to the symplectic affine structure on B coming from the vibration of X check. So there's these vibrations and vice versa. So these vibrations are supposed to exchange these affine structures on the base. And furthermore, so all of this should hold in families. So namely, this shouldn't just hold for one X, it should hold for all X nearby in the complex moduli of X. And then it should yield a sort of surjective map onto the symplectic moduli of the mere Calabi-Yau. So this is one way of seeing that these dimensions should be the same. So in other words, for every complex structure sufficiently close to X, I should be able to do this construction, and I should get a sort of injective map, locally injective map from the complex moduli to the symplectic moduli of the mere manifold. So, so let me just draw the sort of schematic picture here. So in other words, we have some manifold X, here's X, and it's supposed to admit a special Lagrangian torus vibration. So special Lagrangians are half dimensional, half the real dimension. So if this has real dimension 2n, then these tori are n-dimensional torus, n-dimensional tori. So then there's a base, which is again n-dimensional, n-dimensional base. This is B. And then the mere manifold is obtained by just replacing, color. So this is X, and X check. Here's X check is obtained by replacing these by the dual tori. So if this torus has very large volume, then the mere tori will have very small volume. Something like this. And this is also fibered over B. Okay, so this is supposed to be T dual, so the dual torus. Okay, so that's the sort of heuristic picture for how mirror symmetry is supposed to work. This SYZ conjecture is supposed to work. Oops. Okay, so the goal of this talk is to prove that that this conjecture is really true for these examples of non-compact Calabi-Yau manifolds. So namely, if you start with a Del Pezzo surface with degree k, and take a smooth divisor in the anticanonical linear system, then the non-compact Calabi-Yau manifold y minus d is actually SYZ mirror in the sense of the sort of previous slide. So everything that I said will be true to a rational elliptic surface minus a singular fiber of Kodaira type IK. So that is the main theorem that I want to discuss. So what does this really mean? What do we have to prove to show that this is true? So the first thing we need to prove is the existence of special Lagrangian fibrations on both sides of this correspondence with the same base. In this case, the base turns out to be R2. The second thing we need to prove is that, remember this mirror symmetry construction is supposed to work in families, so I should get a map from the complex moduli of X to the symplectic moduli of X check. But it's not entirely clear, since X check is not compact, how to define the symplectic moduli of X check. So the second thing that we need to do, which requires quite a bit of work, is to construct the symplectic moduli space of X check. And then thirdly, we need to construct a map from the complex moduli of X to the symplectic moduli of X check, which exchanges the complex and symplectic affine structures. So I should be clear here that I'm not really proving, I'm proving one direction of mirror symmetry, because to prove the full statement of mirror symmetry, I would also need to construct the same map going backwards. So I would need a map from the complex structure moduli, the complex moduli of X check to the symplectic moduli of X. And that we do not do.
Tristan, may I just ask you?
Yes.
So you don't need to assume anything about large complex structure limits then in your theorem?
So we do, yeah, we do, yeah. So I'm kind of sweeping that under the rug, but in this case, D has to be sufficiently close to and well, that's another thing that we really need to do, because there is no notion of a complex structure limit for these.
Right.
But yeah, so D does need to be sort of sufficiently close to something which is degenerate. So it is there is some notion of large complex structure limit involved.
Okay.
Yeah.
Okay.
Yeah. Yeah, that's a very good question. But actually, it'll turn out that that really we only need that to construct the mirror map. The special Lagrangian fibrations exist even not near the large complex structure limit.
Okay, could it be true without this large complex structure limit assumption?
Yeah, I think that it should be. Yeah, I mean, the only obstruction is the existence of Calabi-Yau metrics on the mirror. That's for where the volume of the fibers is not small.
Because the philosophy somehow is that once you have a special Lagrangian fibration, that should somehow give you mirror symmetry. I mean, is that the philosophy?
Yeah, that's right. Yeah.
Okay, great. Thanks.
Okay, so it's also worth mentioning that the mirror symmetry is now understood to be a relatively broad phenomenon. So in particular, it doesn't apply just to Calabi-Yau manifolds. There's also notions of mirror symmetry for manifolds with effective anti-canonical bundles, and in that case, the mirror is expected to be a Landau-Ginzburg model, which is some sort of non-compact Kähler manifold, which has a holomorphic function attached to it called the superpotential. And then in that case, there's a conjecture of Auroux, which says that that one should be able to prove mirror symmetry in these cases by applying this SYZ mirror symmetry construction to these non-compact Calabi-Yau manifolds. So that was really one of the motivations for our work, was trying to understand how much could be said about this sort of Auroux conjecture for SYZ mirror symmetry. And in fact, our results basically verify all of the conjecture, all of the sort of predictions of Auroux for these examples. Okay, so let me just mention that these examples, Del-Pezzo surfaces and rational elliptic surfaces, are actually very well studied in the mirror symmetry literature, especially as examples of mirror symmetry for non-Calabi-Yau, compact non-Calabi-Yau varieties. So they're very well studied at the algebraic and homological level. So in particular, Auroux, Kotsarkov, Orlov proved one direction mirror symmetry, so the same direction that we're going. This coherent sheaves on a Del Pezzo surface are related to the Fukaya-Seidel category on the rational elliptic surface. And this is recently generalized by Hacking and Keating. There's also this work of Gross-Hacking-Kiel, which constructs mirrors to these objects using the Gross-Siebert program. And then there's work of Lanson-Krzyzewski proving mirror symmetry for Hodge numbers. So again, in this case, it's not really clear how to interpret Hodge numbers correctly. And so there was a proposal by Katsarkov, Katsevich, Pantev for how one should define the Hodge numbers in this example, and Lanson-Krzyzewski proved that Hodge mirror symmetry holds for these two if you follow the KKP proposal for how to define the Hodge numbers. And then there's also lattice theoretic studies by Doran and Thompson for mirror symmetry, sort of lattice theoretic mirror symmetry as well. So this is kind of a common testing ground for predictions in mirror symmetry. So in this talk, I want to try to explain the proof of this SYZ conjecture for these objects. And then I want to explain how to get mirror symmetry for Hodge numbers by defining them sort of differential geometrically, following the sort of classical picture in the compact case. Namely, I want to define Hodge numbers in terms of moduli spaces of complete Calabi-Yau metrics. And then I want to describe some applications. So applications to for example, a Torelli theorem. Okay, so the first thing that I need to discuss, which I tried to mention before, is that these examples don't necessarily, well, they don't, the existence of Calabi-Yau metric doesn't come from Yau's theorem, so one needs to do something more. And on the Del Pezzo side, the fundamental result is a theorem of Tian and Yau, which is much more general than how I'm stating it, but they prove the existence of complete Calabi-Yau metrics. So if you take a Del Pezzo surface and a smooth elliptic curve, so curve in the anticanonical linear system, then they prove that there exists a DD bar exact complete Calabi-Yau metric which I'll call the Tian-Yau metric on Y minus D, which satisfies this Magen-Pair equation and is asymptotic to a model. So when in this producing these non-compact Calabi-Yau metrics, the game is always to find a model for your metric at infinity, and then solve the Magen-Pair equation with that as your sort of target. So let me explain what this Calabi-Yau or Calabi model is. It's quite simple. So you imagine that this a neighborhood of D looks like the normal bundle over D. So we have an ample line bundle over D, and you take a flat metric or a Hermitian metric on E so that its curvature is a flat Kähler metric on D. And then you look at this unit punctured disk bundle in E. So you look at all the sections with norm between 0 and 1. We take the holomorphic volume form with a simple pole on the 0 section. And then you just write down this ansatz, which you can construct by solving an appropriate ODE. So you write down this Kähler form or symplectic form, and then this turns out to be Calabi-Yau and complete at 0. So this is what's called the Calabi model. And this also generalizes to higher dimensions, as does the Tian-Yau theorem. So it's important to say a couple of words about the Romanian geometry. I know this is the Zoom algebraic geometry seminar, but anyways, I have to say something about the Romanian geometry. So the right way to think about the Romanian geometry is that these manifolds are fibered by circle bundles over D, which are just given by the circles corresponding to the sections of length epsilon. And as epsilon goes to 0, these circle fibers collapse, while the base of this manifold is expanding in such a way that the volume of these submanifolds is always a constant. So maybe I draw a picture here. So you have D living at infinity, and these manifolds look like circle bundles over D, which get skinnier but longer in such a way that the volume is always constant. Okay, so the geometry is getting kind of degenerate as you get further and further out into infinity, because you have these circles which are getting very, very small. But yeah, so that's the sort of picture. So it's not hard to see that if you take a special Lagrangian in D, which in this case D is a flat torus, so special Lagrangians are just closed geodesics. So in other words, just lines that close modulo the lattice. Then the circle bundles for each epsilon, if you take the circle radius epsilon over L, then that's actually a special Lagrangian, and it's topologically just the product of L with S1. And these are all special Lagrangian and have the same volume, unsurprisingly, because they're all homologous. So in particular, since D has a special Lagrangian fibration, right? D has many special Lagrangian fibrations. D is just some fundamental domain. You can just take a line which closes modulo the lattice, something like this, for example, and translate it around. These are all special Lagrangians. And for each one of these, the circle bundle in the total space over this circle, over this thing is a torus. So it's S1 cross S1, and it's a special Lagrangian. So in fact, there are many special Lagrangian fibrations of this Calabi model. Okay. So using this model geometry, we prove that that if you have a Del Pezzo surface with a smooth elliptic curve, and you take the Tian-Yau metric on the complement of D, then there is a special Lagrangian fibration of X with base R2. And in fact, there's countably many distinct special Lagrangian fibrations. So for every choice of a simple closed curve in D, so in other words, for every element in sort of primitive element in H1 of DZ, one gets a distinct special Lagrangian fibration, maybe mod plus or minus 1 or something. So there are many, many special Lagrangian fibrations. So what's the idea? Well, the idea near infinity, the idea is clear enough. You have a special Lagrangian fibration of the model. So you just transplant that into the actual Calabi-Yau manifold by a diffeomorphism and a Moser trick. So what you get after this transplantation is something which is a Lagrangian fibration, which is not special Lagrangian, but the fibers are close to minimal in the sense that the mean curvature actually decays quite quickly to 0 as you go towards infinity, because you have this convergence to the model at infinity. And then you prove that you can run the mean curvature flow, and that as long as you start far enough out at infinity, the mean curvature flow actually converges. So then you get something which is Lagrangian and minimal, and therefore special Lagrangian. And then the problem becomes to fill in this vibration from a neighborhood of infinity. So the picture is we have this manifold, which looks something like this. And after running the mean curvature flow, we really have a genuine special Lagrangian torus vibration outside of some compact set. And the question is the main problem becomes to fill in what happens here. But then we have this fact, which is the key thing in dimension 2, which is that if you have a special Lagrangian in some Calabi-Yau manifold with complex structure J, special Lagrangian, so I won't write the other structures, then you can change the complex structure, a different complex structure, integrable complex structure, such that L is a holomorphic submanifold of xj prime. So in particular, after changing the complex structure, this becomes now an elliptic fibration, or a holomorphic genus 1 fibration. And then the idea is that you can use the deformation and compactness theory for J holomorphic curves. So you use the deformation and compactness of J prime holomorphic curves to fill in the rest of this fibration. So basically, once you have a fibration near infinity, it takes a bit of work, but one can prove that you can fill in this fibration all the way throughout the whole manifold. So that's the idea, but it's a very general package. It doesn't really require this package doesn't really require anything particular about the Calabi space. It just requires dimension 2 and some control of the geometry of infinity. Because of course you want to prevent the J holomorphic curves from somehow becoming non-compact or escaping to infinity or something. So anyways, that's the rough idea. Now there's a obvious question then, which is that we started with this, we have this SYZ fibration, and I just said that we can change the complex structure to make it a holomorphic fibration. So this is this hyperkähler rotation trick. So you get this holomorphic torus vibration from X onto C with respect to a different complex structure. So then it's natural to ask where this holomorphic torus vibration comes from, and the result is that you can actually fill in the fiber at infinity of this holomorphic torus vibration by adding an IK singular fiber, and that the compactified space is then a rational elliptic surface. So it turns out that this SYZ fibration of the Tianyao with respect to the Tianyao metric on a Del Pezzo surface comes from the genus 1 fibration of a rational elliptic surface by this hyperkähler rotation trick on the complement. So that's kind of sort of an interesting link between two classical algebraic geometric objects, which comes really from this Tianyao metric. So a question that Yao asked in the 80s is to understand what the symplectic structure of this hyperkähler rotation is. So it's well known that if you have a Calabi-Yau structure, that you get this hyperkähler on a surface. You get its hyperkähler structure, and so Yao asked what the symplectic structure of the hyperkähler rotation was. So I'll try to come back to this question shortly. So that sort of takes care of the Del Pezzo side. So on the so now we need to prove the same thing, or at least roughly analogous results for rational elliptic surfaces with an IK fiber in order to establish at least the existence of SYZ fibrations as the first step towards SYZ mirror symmetry. So the first thing I need to discuss in order to talk about what happens on the rational elliptic surface side is the existence of Calabi-Yau metrics. So again, I need to explain what the model geometry is. So the model geometry is quite easy. It's just a punctured disk with C mod a holomorphically varying lattice. So you see there's this log Z term, which gives you the sort of monodromy representation. There's a natural holomorphic volume form here with a simple pole on the central fiber. So here kappa is some holomorphic function, which is non-zero at 0, but let me just assume kappa is 1, just to make our lives a little bit easier. So so this is the model geometry, and how do you identify an elliptic fibration with an IK fiber over 0 with this model geometry? Well, you just take any choice of section of this elliptic fibration, and it doesn't even have to be defined over 0. Then you just use the fiber-wise Abel-Jacobi map, and you can identify X with X mod. So what I want to emphasize here is just that there are many ways to identify given elliptic fibration with an IK fiber with this model space, and they correspond to choices of sections over the punctured disk. So in this case, Green, Shapir, Vafa, and Yao wrote down a Calabi-Yau metric on this model space, which is flat along the fibers. So you can think of this, so you have some Ricci flat metric, which restricts on each fiber to the flat metric on the torus fibers. So they called this a semi-flat metric. And here's a formula for it. It's very complicated. It's sort of irrelevant, but I just wanted to convince you that such a thing exists. So once you have this semi-flat metric, you can pull it back by any identification. So if you have this fiber-wise Albert-Jacobi map for any section, then you can pull back this semi-flat metric by this identification, and you get what I'll call the semi-flat metric with respect to sigma. So with respect to this choice of section. So there's also a special Lagrangian fibration here. So you just take circles in the base, and you take, again, it's the same picture that I drew before. You just slice the torus by the imaginary part of x equals a constant lines. So that turns out to be a special Lagrangian fibration of this model space. So Hein proved the existence of Calabi-Yau metrics in this case. So his theorem, so he developed a lot of technology and proved that much more than what I'm going to say, but let me just explain what his theorem says in this case. So you take this rational elliptic surface with a IK fiber at infinity, and you take the homology class of this bad cycle. So this torus that I've described here, say for R equals 1, it doesn't matter which one, they're all homologous. So if you take any Kähler metric on the complement, which pairs to 0 with the bad cycle, and which has finite volume, then his theorem says that you can find a section and some positive number alpha naught, such that for all alpha bigger than alpha naught, there is a Calabi-Yau metric in the Bott-Schrödinger homology class of omega naught, converging exponentially fast to this rescaled model at infinity. So this is where this large volume limit comes from. As you see, this alpha here is related to the volume of the fibers, more or less, after smoothly rescaling. Okay. So in particular, the main so one way to generate this is you just take any Kähler metric restricted from the actual rational elliptic surface, and then you can apply this theorem and get lots of Calabi-Yau metrics asymptotic to this semi-flat metric at infinity. So from the point of view of setting up the moduli problem, there are three things that I want to highlight here. One is this pairing to 0 with the bad cycle. So there's a sort of cohomological condition here. The second is that this thing has finite volume. And thirdly, that the theorem sort of asserts that there exists a section, and that this section actually appears in the model at infinity. So there are some things here which make it a little bit hard to set up the parameter space for the moduli problem. So yeah, so let me explain what the main sort of outstanding questions are. So the first question is that the actual de Rham cohomology of X is dimension 11 minus K. But this condition of cutting out of pairing to 0 with this special Lagrangian, or this Lagrangian section at infinity, this cuts out a 10 minus K dimensional hyperplane. So it's natural to ask whether there are Calabi-Yau metrics in the remaining 1 dimension worth of de Rham classes, which is what you would expect if you naively expected Yau's theorem to hold. Secondly, from the point of view of the moduli problem, this construction that Hein's theorem depends on, in fact, leaves open the possibility that there could be, in fact, infinitely many distinct Calabi-Yau metrics, even in a fixed Bott-Schrödinger class. Just because it proves existence, it doesn't prove anything about uniqueness. But furthermore, even if you knew that there was a unique unique Calabi-Yau metric in each Bott-Schrödinger class, this Bott-Schrödinger homology is, you can calculate its isomorphic to the de Rham cohomology across the space of holomorphic functions on C. So that's a wildly infinite dimensional space. So in particular, even if you knew the uniqueness in the Bott-Scherring cohomology, it's still not really great for defining Hodge numbers, because the dimension of this space would be infinite. So we can't just define the Hodge numbers in the sense of Bott-Scherring cohomology. So this is maybe one reason why Katsarkov, Kontsevich, Pantev gave several proposals for how to define Hodge numbers. So their proposals are purely algebraic. They were in terms of sheaves of logarithmic forms, weight filtrations, perverse sheaves, etc. So I think they had three proposals. And these were calculated for these examples by Lunson and Przalkowski, and on both sides they yielded 10 minus k. So that proves this mirror symmetry for the KKP Hodge numbers. That both sides of this correspondence you get 10 minus k. Okay, so there's one. So to answer this question about the Calabi-Yau metrics in all the Kähler classes, and the remaining one dimension that was not mentioned by Hein's theorem, I need to discuss sections. So sections in this case are just multi-valued functions, which have some integrality properties of these coefficients of log z and log z squared. But actually, it turns out that if you relax these conditions, so if you just assume, if you relax these conditions from integrality to rationality, or even just real, then these correspond to multi-valued sections. And in fact, they're finitely many valued for Q and infinitely many valued for R. But it's not hard to check that if you pull back a semi-flat metric by a multi-valued section, so you can view this multi-valued section as giving you a map from the universal covering space to the universal covering of the model space, then actually the pulled back semi-flat metric is invariant under the sort of transformation group, so it still defines a semi-flat metric. So I'll call these non-standard and say that they're quasi-regular when it's infinitely finitely many valued, and irregular when they're uncountably many valued. So then in the quasi-regular case, at least there's still special Lagrangian bad cycles. They just are tori, but they project to the base, covering the circle more than once. So you have to go around several times to get them to close. But actually the irregular objects, so the irregular semi-flat metrics, they cannot admit any special Lagrangian vibration just due to sort of topological considerations. Okay, so with all of that, then the theorem that we prove, which is just this let me just partly as a restatement of Hein, but there's this one extra addition, is that if you have a rational elliptic surface with an IK fiber, then for any Kähler metric on y minus d, you can find a multi-valued section and some parameter alpha naught, such that there exists a unique Calabi-Yau metric in the Bott-Scherring cohomology class of omega naught, converging to this rescaled semi-flat metric. So the existence part is just Hein's theorem once you identify the model metrics, together with this sort of minor improvement that if you look, there's no assumption that omega naught has finite volume. So that's sort of a minor point. But the uniqueness is really the new result, and this is the thing which is essential for doing mirror symmetry. And the uniqueness follows from essentially optimal uniqueness theorem, which I'll mention again below on the next slide, I think. And this says that the parameter space for the Calabi-Yau metrics is asymptotic to the parameter space for Calabi-Yau metrics asymptotic to semi-flat metrics is at least equal to the cone of Kähler classes in the first Bott-Scherring cohomology. So it's at least infinite dimensional. It's infinite dimensional, but at least it's sort of we have a well-defined parameter space. So this is an improvement from the point of view of setting up the moduli problem. And actually, it turns out that these quasi-regular metrics are do actually play a role in mirror symmetry. Okay, so with this, we can answer this question of Yau, which is what is the symplectic structure on the hyperkähler rotated Del Pezzo surface. So we take any element of the first homology of class of the torus of a elliptic curve in a Del Pezzo. Then you get this SYZ fibration, you hyperkähler rotate so it becomes holomorphic. Then the symplectic form of the Ricci flat metric turns out to be one of these semi-flat metrics produced by the previous theorem. And the only case when it's actually one of the standard semi-flat metrics is when the torus D at infinity has this very special square lattice structure, and gamma is one of these special cycles generating the lattice. So in fact, you almost always get quasi-regular, and generically these things are irregular. So that's a kind of an interesting observation, and that was actually why we realized that we needed to find these irregular Calabi-Yau or irregular semi-flat metrics, is because after hyperkähler rotating from the Tiano metric, you essentially never get a symplectic form which admits a special Lagrangian fibration. So that was why we knew they had to be there. Okay, so what's this uniqueness theorem? So the uniqueness theorem is actually stronger than what I said. So it says the following. So if you have a rational elliptic surface with an IK fiber and two Calabi-Yau metrics which solve the same Monge-Ampere equation, and they have the same de Rham cohomology class, and suppose that they converge at a sort of optimal polynomial rate to some semi-flat metrics at infinity, so different, in principle, different semi-flat metrics. Then there exists a fiber-preserving map, which is homotopic to the identity, such that if you pull back omega-1 by omega-2 by f, you get omega-2. So this says that the uniqueness, so Calabi-Yau metrics, in Bott-Chernin cohomology, it's infinite dimensional, but now we have this infinite dimensional automorphism group, which just comes from basically translating along the fibers. And the theorem says that if you mod out by that automorphism group, then you get just the de Rham cohomology as the moduli space of Calabi-Yau metrics. So in particular, this allows us to define a sort of moduli space of Calabi-Yau metrics. So the issue causing the infinite dimensionality before was just this large automorphism group. Okay, so okay. Okay. So the same result, this existence of special Lagrangian fibrations, also holds for these rational elliptic surfaces, at least when there's no topological obstruction. And the argument's exactly the same. So now you can prove, with this, you can prove SYZ mirror symmetry. So you can, so we start by finding a special Lagrangian fibration on a Del Pezzo pair by this vibration theorem. Then you construct a topological mirror by using this hyperkähler rotation trick. And then you identify the correct complex structure. This is using a Torelli theorem of Gross-Haken-Kiel. Basically, in our setting, there's a distinguished point of the moduli space, which is determined by the period integrals. So that determines the correct complex structure for the mirror. And now this also admits a special Lagrangian fibration by the fibration theorem for rational elliptic surfaces. And then you can just compute because you chose the point in the moduli space correctly using this Torelli theorem, you can show that mirror symmetry exchanges these complex and symplectic affine structures on the base of these SYZ fibrations. This is a calculation. Now to compare the Kähler classes. So the Kähler class always lies in some 10 - k dimensional subspace, pairing to 0 with one of these special Lagrangian fibers at infinity. So there's some lattice polarization issue going on here, but this means that the Kähler moduli space is 10 minus k dimensional. And on the complex side, so in other words, these are all this sort of classes which admit Calabi-Yau metrics asymptotic to some quasi-regular semi-flat metric. And on the complex side, the complex moduli of Del Pezzo pairs is also 10 minus k dimensional. And both of these numbers agree with the KKP Hodge numbers. So the sort of classical differential geometric approach to defining Hodge numbers in terms of moduli spaces of Calabi-Yau metrics turns out to agree with the algebraic approach of Katsarka, Kontsevich, Pantet in this case. So going the other way, is an interesting question. I think the main issue is understanding the symplectic moduli of Del Pezzo surfaces. And then finally, let me just mention, so that as a sort of application of this work, we prove this Torelli theorem. So which says that if you have two rational elliptic surfaces with singular fibers of type IK and two Calabi-Yau structures with the asymptotics being semi-flat metrics, then if there is a diffeomorphism from one of these objects, one of these non-compact Calabi-Yaus to the other, such that the pullback of the holomorphic volume form is equal to omega 1 just in the Durand cohomology, and same for the symplectic form, then in fact you can upgrade this to a diffeomorphism which pulls back these structures pointwise. So not just cohomologically. And in fact, it's this assumption about the rational elliptic surfaces you can just remove, because there's work of Sun and Zhang that says that actually the only thing you really need is to assume that these omega i's are L2 integrable and that they have a certain volume growth rate. Well, it's maybe a certain, slightly more than that, but basically what we prove is a Torelli theorem for these ALH star, what they call it, ALH star gravitational instantons. So it says that these objects are really classified just by the cohomology of their Kähler form and holomorphic volume form. So anyways, I will stop there. Thanks.
Great, thanks a lot, Tristan. Questions?
When you're constructing the dual, so you're getting this base B, is it like, is this unique, or is it possible to get B and B prime, like two different bases, and then get two different duals and get that, then those duals have to be the same?
So B and B, so the base should always be the same. I mean, they're not canonically identified, of course, because I mean, really the two bases are just R2. So until you have the, so it's a little bit, so there's something in this SYZ picture. So SYZ says that you should really take this special Lagrangian fibration and just do this T duality like fiber-wise. So then there should be a sort of canonical identification of the bases. But that seems a little bit hard to do in practice. So what we really prove is that the rational elliptic surface and the Del Pezzo both have fibrations onto R2, and that and R2 comes with two different affine structures, and the affine structure, the symplectic affine structure of the Del Pezzo side is equal to, or the complex affine structure of Del Pezzo is equal to the symplectic affine structure of the rational elliptic surface. But yeah, there's no, in general, like we don't prove that these bases are canonically identified.
Thank you.
So I have a question about, I think it was on page, slide 32.
Okay. 32. Okay, here.
Yeah, so are you saying here that if you take the complement of the anticanonical divisors on the Del Pezzo and on the rational elliptic surface, that complex structures on those are related by a hyperkähler rotation?
I'm saying that one can pass from a, what am I saying? So what I'm saying is that if you start with a Del Pezzo surface, you can construct at least the topological mirror by a hyperkähler rotation. So there's some, rational elliptic surfaces with an IK fiber, basically there's the families, the deformation families match the deformation families of Del Pezzo surfaces of degree K. So if you have a degree 8 Del Pezzo surface, there are two distinct deformation families of rational elliptic surfaces with an I8 fiber at infinity. So then it's a little bit of a question about how to match these two families so that you end up in the right deformation family, and the right way to do that is by hyperkähler rotation. So I'm just saying that hyperkähler rotation somehow identifies the right topological family, but it does not necessarily identify the right complex structure on the mirror manifold.
But isn't the hyperkähler rotation isn't that a question of rotating the complex structure in a twistor family?
Yeah, that's right. Yeah. So I'm just saying if you start with well, okay, maybe I'm not understanding the question, but I'm saying that if you start with a Del Pezzo surface, then I can hyperkähler rotate, and I get a complex structure, which is actually, so that new complex manifold actually compactifies to a rational elliptic surface. So then I land in some other family, which is coming from a rational elliptic surface, and that family is at least topologically the right mirror to the Del Pezzo surface.
Okay, yeah, okay, but you still may have to change the complex structure further to get.
Yeah, exactly. So that's why we need this Torelli theorem, because actually you just get the right topological mirror, but you might not be in the right place in the complex deformation space to be the right mirror. So that's why this Torelli theorem becomes key for identifying the right complex structure. So really the only issue here, the only thing that's happening is in degree 8, because for any other degree there's a unique deformation family. So then there's sort of can sort of ignore this hyperkähler rotation trick. But the hyperkähler rotation in degree 8 is the thing that makes sure that P1 cross P1 is mirrored to the right rational elliptic surface, and blow up of P1 at a point is mirrored to the right other family with an I8 fiber.
Okay, thank you.
Okay, no further questions? No? Okay, thanks a lot, Tristan. Great talk.
All right, thanks. Thank you.
And bye, everybody. Bye.
All right, see you.
See you.